And then we'll deploy Qwen 3 model and fine tune it using the same infrastructure. But before that, I want you to first understand when to even self-host, like when do self-hosting make sense. So for most use cases, starting with an off-the-shelf API is very quick and easy to get started. But there are various scenarios where self-hosting is very important and it can give an edge to your business. So for example, the number one scenario is performance. So one of our customers actually fine-tuned a personalized LLM to match each user's pricing style. And they started off with prompting GPT-4o and fine-tuning it, but it was not able to match the accuracy expectation that they had. Then they later switched to fine-tuning the Llama model, and the accuracy gains were really, really good. Turns out that the data that they were collecting from the users was very personal. So they would connect to your users' email account and documents, and they would fine-tune a specialized model specifically for them. And if you're dealing with data that's not on internet and general models are not trained on it, then fine-tuning a Llama is much more easier and it has a lot more accuracy gains. Second scenario is when you're building applications that have strict latency requirements. So, for example, voice AI is pretty popular these days, where every millisecond matters. And in such scenarios, if your entire application is hosted in your own cloud, let's say a particular region, and you're making API calls to the model provider, which is residing in a different infrastructure where you don't have any control, then the latency increases and it leads to a bad user experience. And especially with today's agents where you have multiple calls within the same workflow, it adds even more. So self-hosting the entire voice AI stack with all the STT, TTS workers and LLM at the same in the same region, and in some cases even on the same node, can significantly reduce the latency and increase your user experience. Third scenario is narrow tasks, especially function calling in agents, and that is the example we will be covering today. So basically, NVIDIA released a paper called Small Language Models Are the Future of Agentic AI recently. And the premise of that paper was that when you are building multi-turn agent workflows, where you have a general purpose model for planning and various smaller models to call some function calls, then small models performs better, and using an off-the-shelf model which is larger is usually a waste of resources. And in the diagram, you can see that we are using a general purpose or large model for the reasoning task and the planning task, and smaller models to call functions, which you can fine tune very easily. And the fourth and last one is data security. So if you are in spaces where data security is very important, even to get your business off the ground, such as like healthcare, legal, finance, and defense, then self-hosting AI models and your entire AI stack becomes even more important. So assuming that you fall under one of these scenarios and you decide to self-host, let's see what all expertise you will need in order to deploy your model in production. So you will need bandwidth on two fronts. One is the AI expertise, and the second is the infra expertise. Under AI expertise, you will need to select the right model. Then you will need to understand what is the right fine-tuning technique for your use case, such as supervised fine-tuning or RLHF. And then set up evals because your production data is continuously changing. And anytime you make a change, you need to know whether it is right or wrong. And the second is infra expertise. So in order to take all this, your model and your fine tuning, and scale it up in production, you will need to select the right container orchestration framework like Kubernetes. You will need to set up auto scaling, load balancing, and setting up CI/CD. Now, both of these things require significant time and engineering expertise. However, only one creates a differentiation in your product, which is your AI expertise, right? How well is your model running? How well have you fine-tuned the model? How well are your evals quickly determine any data drift that is happening? And that is why we want you to focus solely on the AI side of things while we take care of the infrastructure. And this is what this workshop is about. We will look at how to provision an infrastructure which will help you quickly productionize any model, and we will specifically focus on doing this on readily available GPUs. So most of the people that we talk to think that they will need higher end GPUs like H100s and GB200s to productionize. That is not true for all the use cases. In fact, here I have a small table which shows you that you can run models of any modality on these on-demand GPUs. So if I talk about text, then you can run any model up to a 150 billion parameter without any quantization on L40S. And these are available on demand and are actually cheap. Talking about audio, you can run literally any STT or TTS model, the latest one like OpenAI Whisper or NVIDIA Parakeet, and the latest Voxel and Orpheus model as well. And then you can run various embedding and OCR models because they are very small, and you can run it on high concurrency. So on a single A10, you can host probably 20 or 30 copies of these small models. So this is what we're going to focus on demand GPUs. And that's it. So this was a brief context. So first we will configure the infrastructure, then we will deploy Qwen, and then we'll fine tune it. Yes. So during the process, if you want to share some links or exchange some commands, you can just join our community, and there you will find a channel called AWS Events. You can join that channel. Yep. So with that, we will start with, I'll hand over the mic to my co-founder Samagr, and we will start the process.
Hi guys, welcome. So I hope you understand when to self-host and when not. So what I'll do is I'll walk you through the entire process from scratch, walk you through the code that I have written and how to extend it to your own use cases. So let's get started. First of all, I have created an entire guide on GitHub, which you can follow along if you feel left behind. If you go ahead and search Tensorfuse examples GitHub, you will come across that. Let me know if some of you are unable to find it. This is the repo, and inside this there is this folder called function calling fine tuning. So in this there is an entire guide which you can follow if you are left behind. So is everybody okay with the link, or do I need to send? Okay, cool. So the first step is to essentially configure and sign up on Tensorfuse. So I'll just do that and explain what happens behind the scenes. So let me just sign up and complete the onboarding. Yep. So right now we are completely on AWS. So the first step is to connect your AWS account to Tensorfuse. And for the duration of the workshop, it will cost you around $5 to $6. Tensorfuse reserves some resources on which the control plane of Tensorfuse sits on your cloud account, and that costs around $300 per month, which goes from your AWS credits. None of this goes to Tensorfuse, but it is the cost of resources which Tensorfuse provisions. So let's go ahead and see how to get started with the cluster. So first of all, I will log into the console. I would recommend using identity center user.
By the way, if you need time or if you want him to pause, you can just say him that yeah, just in the process. So he'll pause.
Yeah, I'll stop. Okay.
Probably you can take confirmation.
Yeah.
If they are done with this time.
Okay. Okay. So when you are logging in, I recommend you to log in with the account with which you have permissions to create stacks and IAM roles. So I am logging with an administrator access. This account has all the permissions I need, but you can log in with either an IAM user or an identity center user. Once you log in, you will
help with login as well.
Does anybody need help with login? No. Okay. So on the top, you will see your account ID. This account ID is needed by Tensorfuse to provision resources. So what you can do is you can copy this account ID and paste it here by pressing continue. Once you enter AWS account ID, it will ask you to grant permissions to Tensorfuse to provision resources on your cloud. So once you click grant permission, you'll be taken to a screen where again you can choose the previous user that you logged in with, and you will see an approval screen. So basically this screen creates IAM roles for permissions which are needed to run Tensorfuse. You can go ahead and check in detail what these permissions are by clicking on View Template. So here's the entire list of permissions. To approve, I'll go ahead and click I acknowledge that AWS CloudFormation resources can be created. And then I'll click on Create Stack. So this process should start creating a stack called TensorCube Access Stack on your CloudFormation. So this is the stack that is being created. The purpose of this stack is to allow Tensorfuse to access your AWS resources and create the cluster. So this can take up to 5 to 10 minutes. For me, it's permissions are granted. For you, it might take 5 to 10 minutes. So once it is done, it would actually create two stacks. One is called stack, and the other is called TensorCube Granular Permission Stack. Hi guys. And once this process is done, it will show permissions granted in your cluster.
Don't mind.
Yeah.
Can you guide us to this is through Tensorfuse, right?
Yes.
Not through the AWS UI.
The Tensorfuse app.
No, this is through TensorFuse. Agam, can you help those two guys?
Yeah.
If this process failed, is there like an alternative that we can use instead of AWS, like our local cluster, or not necessarily?
Yeah, I didn't get the
So
GPU.
the setup is slightly
for the
different.
standard instance though.
That is present in our docs, but it would require you to create and deploy Helm charts on your cluster.
Yeah.
We do that, but it would take time. We like it would be out of the scope
Yeah,
for
yeah.
right now.
Okay, no worries.
But we have a list of Helm resources that can convert any cluster.
I need to check. I'm sorry.
Ready for
Do you have
Okay.
an-
Yeah.
Is this workshop going to be uploaded as a video? Or
yeah.
awesome,
In a few days.
awesome, that's great.
So, while these permissions are being granted,
Thank you.
I just want you to understand what all things we are going to provision in your AWS account so you get an idea of what exactly is the $300 cost for and what exactly is happening. So our goal is to enable two use cases, inference on models and fine tuning. Now for that, at the heart of this infrastructure is a Kubernetes cluster. So at the center, you can see an EKS cluster. And what we have done is we have fogged all the popular open source projects, KDA, Knative, and Istio, and modified them to work for inference use cases. And I would come to what it means to modify them for inference use cases. So everything is battle tested and reliable and works for AI inference. Along with that, we also provision certain resources like CloudWatch for logging and monitoring, S3 for storage, and a load balancer to give you URLs and a certificate manager to give domains and stuff. So once is permissions granted for everyone who is following through? Okay. So what I will do is I would select a region in which you want to create a cluster. You can create a cluster in any of the regions. TensorFuse works across all availability zones within a region to optimize for availability. So sometimes AWS goes out of availability in a particular availability zone. So we migrate your deployments to other regions. But we recommend creating a cluster in US East 1 so that you have maximum availability. And at the same time, this is the email that you want to receive alerts to. So for example, if a new deployment goes up, a deployment fails, there is some failure in your fine tuning runs, this is where you would start receiving the emails. And once I click this, I would have to click on configure cluster, and it would start creating the infra that I talked about on AWS. So if I go to CloudFormation, hit refresh, I would start seeing a TensorCube base stack, which would automatically get created for you on your account. Now this process is slightly longer. So while this happens on the background, let's go through the code that we are going to run today and understand what is happening behind the scenes.
Perfect. Thank you.
So why are we doing all this instead of running a Kubernetes cluster? So that's what I want to cover. So a good inference infrastructure essentially focuses on four things. One is cold starts, auto scaling, load balancing, and integration. So if you remember the CPU era for which Kubernetes was optimized, you had very small images, Docker images, container images, which were around 200 MBs in size. So they had faster load times. The auto scaling bit was also very simple. If you had high CPU utilization, high memory utilization, you would start more servers, or you would add more machines to the service, start up more pods, and you would be okay. Third is load balancing. Load balancing refers to where, so let's say you're running 10 servers. So what server are your requests being directed to? That's what load balancing means. And earlier when requests were stateless, they were simple HTTP request, you would just do round robin distribution of requests, or you would hit the server which needed least requests. That would work very well. And as far as integrations are concerned, this Kubernetes server would work well with Nginx, UVCon, GUnicorn, etc., which are very common, which had a very common interface. So all was set, but things have changed as far as AI models are concerned. So now instead of sorry, that's wrong. That's not small images. Instead of small images, you have very large images, around 20 gigs in size. So now you have lost the ability to download them within, let's say, 5 seconds, 6 seconds in order to start your pods. Auto scaling has also changed a lot. So if you want to scale up your system, you want to look at metrics which impact the SLA that you have given to your user. So for LLMs, your throughput or inter-token latency in some cases, or time to first token. So if you are running voice AI models, then you need time to first token to be very fast so that it doesn't feel that you are talking to anyone. Similarly, time to first byte, it is very important for people running TTS and STT models. So also during the CPU era, the same Docker image can run across all kinds of CPUs, but now you have different GPUs, A10Gs, L40S, and then there are custom chips like Inferentia and Trainium from AWS. So traditional Kubernetes does not work well with all the heterogeneous compute that is available.
So this is the AWS.
Third is load balancing. So now if you would load balance in a round robin manner, your requests might start to congest a particular server. That is because each request has different processing times. So for instance, you are having an agentic use case and you are hitting an LLM. So one of the requests can have very small context where you're not pulling any data from RAG pipelines and just asking a simple question. So that request will take less time. But another request might have the context of an entire database to query from. So your requests are not homogeneous and are not stateless. And therefore, using round robin balancing will fail because you would start congesting. It might be possible that a server is already serving few very large requests, but you keep sending requests to that server because you are thinking that it has less number of requests. So the right metrics for load balancing become KV cache utilization and inference server QLength. So KV cache is essentially, so when LLMs run, they cache previous tokens so that they save the processing of all those tokens till now and start processing from the current token itself. So all those metrics combined should inform your load balancing and routing decisions.
Yeah, second step.
And finally,
it will create the entire Kubernetes cluster.
There are specific servers now for serving specific use cases. For example, if you want to serve LLMs, you would need vLLM, SGLang, etc.
So it's created.
Dynamo is for very large scale use cases. Then you have TGI, Triton Inference server. So these servers have to be integrated with your infrastructure in order to inform these auto scaling and load balancing decisions. So all this has changed. And what Tensorfuse does is a provisions infrastructure which is optimized for the GPU era along all these lines. So you would instantly download images, even if they are like 80 gigs in size, within 1 second. Your containers would start within 1 second. You would have option to auto scale on the basis of all the LLM metrics or on STT metrics or TTS metrics. You won't have to engineer all these. And then you can do load balancing on KV cache utilization, inference server queue length, etc. So all this is what Tensorfuse handles.
Will enable us to deploy everything.
And when we talk about fine-tuning infrastructure, there are so fine-tuning. I'll tell you how enterprises and companies usually run fine-tuning. So a lot of our customers, what they do is train very small LoRa adapters. Are all of you familiar with what a LoRa adapter is? Okay, so they are, think of it as micro attachments that can modify your model slightly and they can be loaded instantly on demand. So a lot of our customers have an infrastructure setting where for each customer they serve, they train a LoRa adapter and serve with the same base model. So that is an example of fine tuning, which people might need. So our most popular use case is from a customer who are training models for writing styles so that it feels that the emails are coming from you, the marketing content is coming from you. So what he does is he takes in the writing of a particular company, the brand itself, trains a LoRa adapter on it, and then pushes the LoRa adapter to do the work. In that scenario, you would need the same base model, same kind of fine tuning strategy, but what you want to do is run the same job multiple times. So for a good fine-tuning infrastructure, you just need three things. One is a queue to handle all these fine-tuning jobs that are coming in. You need storage, fast storage or integrations with Hugging Face or S3, which can hold those LoRa adapters, and multi-GPU training, which essentially enables you to train LoRa adapters of higher rank or higher alpha. These are hyperparameters that you set during training, and at the same time enables you to train on larger models. You can train 70 billion parameter models, 109 billion parameter models for these. So this is what makes a good fine-tuning infrastructure. And the diagram that I showed you earlier actually provisions that same infra for you in your cloud so that you don't have to think about all the nuances that I mentioned here. So this is what we are doing in the infra that we are setting up. One last thing is that I want you to understand whenever you are doing self deployments is cold starts. So cold start is one of the reasons why people don't prefer self-hosting, because an API can be very quick. But most of the problems with cold starts can be easily solvable with slight tweaking, and we have solved almost all of them. You just need to set up the correct configurations in order to serve models with very low cold starts. So a cold start basically consists of four things. And when I say cold start, when in popular market speak, if you say cold start, people are usually talking about how their containers start. So from the moment a request went to start a container to when the container came up, that's what cold started. But usually in deployments, that's not what your customers will care about. Your customers will care about the time when they start receiving responses to their requests. So I'm talking about that cold start from an SLA perspective. So cold starts basically have four components to them. One is the node startup time, when a machine from AWS connects to your cluster. Second is the actual container start, when the machine starts up and your container boots up. So your Docker file gets loaded and starts up. Then you have the model loading. So model will be loaded either from your S3 storage or your Hugging Face storage or wherever your model store is. And then there's this fourth step called graph capture or TF compile. Have you guys heard of it? So essentially, what this step is that this step is meant to optimize a particular PyTorch model for the hardware it is running on. So the advantage you get from this is that if you are receiving a tokens per second of, let's say, 10 tokens per second, if you do graph capture, that would jump up to 50 tokens per second because your PyTorch model is optimized to run on that particular infra. So these four steps are what happens before you start serving a model. And the first step depends on your cloud, which is where your nodes come from. So AWS, it's very fast, but if you go to other clouds, it's very slow. Like other clouds, I have seen node start times of 2 minutes to 15 minutes on other clouds. Container start would depend on your orchestrator. So orchestrator could be Kubernetes. A lot of people use Slurm these days in research labs and stuff. And the last two parts depend on the inference server you're using. So for example, vLLM is an inference server. It is responsible for downloading the model and running the graph capture part. So these are the standard metrics that I have seen. So node start would take around 30 seconds, container start. So if you start a container with vLLM base image, it would take you around 15 minutes from Docker Hub and from AWS ECR as well. That's because you have to download all the NVIDIA libraries, the container runtime, and all the PyTorch files on the machine to start. So it will take you around 15 minutes. Then models these days are like 100 gigs to 200 gigs in size. That will take you around 10-15 minutes if you go via regular channels. And the last time graph capture, depending on the model, can take anywhere from 30 seconds to 10 minutes. So that's what used to happen. The infrastructure that we are setting up will solve 3 out of the 4 problems that we have here. So we allow very easy over provisioning. So if you don't want to over provision, it would still stay at 30-second node start. But you can always over provision 10% of your pod so that your node start feels almost zero. The major work that we have done is reduced container start times from 15 minutes to 800 milliseconds. And how we do that is because of a crucial fact that 76% files in your container images are now never actually loaded. They are never used. So what we have done is we have created, so Snapshotter, when Docker runs a container, Snapshotter is the component that is responsible for creating the file system for that particular container. So it would download the image, it would unpack the image, uncompress the image, and then create a layered file system and present it to the container key. This is your root, start from here. Now, since most of the files will never be loaded, we have built a lazy loading snapshotter, which starts containers instantaneously. And with every run, it optimizes which files to download first. So you always download files which are most important and most useful during the start time. So it starts instantaneously. For model loading, what we do is we have very good integrations with things like Hugging Face Z and HF transfer. Now these libraries, what they do is use the entire bandwidth of a node to download the model. So you can get download speeds of 1 Gbps to 10 Gbps depending on the node configuration on AWS. Now the last part is something that is out of our control and depends on the inference server. vLLM is already working on improving graph capture times and they are trying to bring it down. The PR is already underway and it would get released within like a couple weeks. So for that, for graph capture, we might need to wait for them. So you go from around 30 minutes to start a new pod while scaling to 1 minute if you use Tensorfuse and do configurations properly. So that's what we are trying to provision.
Random question. I'm wondering if y'all are aware of modal and how this compares to modal.
Yeah, so think of us as modal running on BYOC version of modal. So what modal does is they also have a snapshotter that they have built.
Yeah.
And they can start containers very quickly. So very similar to modal.
Yeah.
The only advantage with us is that we stay within your AWS cloud, so you can use your AWS commits.
Yeah.
The data stays within your VPC.
I see.
And everything is under your control. So you can tweak parameters whenever you want, however you want. So all those flexibilities are available. The Modal guys have done a very good job. They were, in fact, the first ones to bring to market the idea that containers can be started very quickly.
Yeah.
So we have learned a lot from them as well. Okay, so we are at 19%. So what I'll do is, by the time this is getting completed, we'll set up the code to actually deploy and run the models. So let me just open a terminal. And I'll go ahead.
So, Samak, are we cloning the repo?
Yeah.
Yeah. So yeah, I think you can just now follow from here. Yeah.
Guys, if you are left behind on the repo, I have a README file that you can follow, whatever step you are. So let me just go ahead and clone this repo. This repo has a lot of different examples that you can host. So there are Deepseek, text-to-image, TTS models, everything. We will be focusing on function calling, fine-tuning part of the repo. Let me just clone it.
I actually have a file.
And
So I don't mind following.
yeah, let me just.
Just I mean, I'm because I don't think I can find it.
Is the code
I
visible to everyone?
checked with Tensorfuse examples. I'll get that.
No, I just posted on Slack as well.
So let's understand what we are trying to do. So today we are trying to fine tune the Qwen 3 8 billion parameter model for function calling. So this is the model that we will be fine tuning today and deploying. And we will be using the Hermes function calling dataset. So let me just open that up as well. So this is the dataset that we will be using. And our goal today is to modify a reasoning model for agentic use cases to function call. Now for agentic use cases, reasoning models don't work great because they have a lot of think tokens and they are token hungry. And in agentic use cases, you have a lot of input context to process. So it is recommended that you don't use a reasoning model for function calling when you're using agents. And second problem with smaller models, not the frontier ones, is that they are very bad at function calling. So they won't parse the JSON properly, or they would misplace the arguments or call functions via wrong names. So what we are going to do is we are going to convert this Qwen 3 8 billion parameter model, which comes with think tokens and everything, to a function calling model which just outputs a sequence of action steps. So let me just quickly show you how the data set looks like. So this is how our data set looks like. We have some description of all the functions that are available to the model. So you see this tool stack, it lists different functions that are available for the tool to call. The human asks a query. I recently installed a new security system at my home. I want to ensure everything is functioning as it should. And in the end, asks to perform certain steps. So it asks to start a 30-minute recording of the live feed from the front door camera. Retrieve the recorded feed from the front garden, focusing on the time period between 15 and 1700 hours on April 22. And that's the query. So the AI model needs to understand the tools available, understand the query, and it needs to generate a set of tool calls. So for example, for our query, it would call the camera of the front garden with a particular start time and particular end time and get the recorded feed from there. That's the kind of outputs we want from the model. And we would be using a very good fine-tuning library called Axolotl. I'm sorry, Axolotl. So I'll briefly touch on what Axolotl is. Give me just 1 second. So yeah. So for most use cases, you don't need to write any imperative code in order to do fine tuning. Most of the times, what you can just do is specify the base model you are trying to train, the fine tuning technique that you want to use, and the data set that you want to train on, and just run the training. And that is enabled by this library called Axolotl. Unsloth is also another library which a lot of people recommend. We have integrations with both of them. But as far as the ease of use is concerned, Axolotl is very popular because you just need a YAML in order to run the fine tuning. So today we will be using Axolotl to train and fine tune the model. And we'll be using vLLM as our server for hosting these LoRa adapters and fine-tuned versions of Qwen 3.8b. So let me just check how far we are on our configuration bit. So yeah, it's 48% complete. So let's walk through the code first. Okay. So there are 3 folders: evals, fine-tuning, and inference, and we do exactly what they're named. The first folder defines the evaluation script. All the fine-tuning code is in the fine-tuning folder, and all the inference code is in the inference folder. I would come one by one to all of these. So first of all, whenever we are trying to fine-tune a model, the first thing that we need to do is to define an evaluation criteria, because otherwise we won't have an idea of whether our model is performing well or not. So in this scenario, I have taken a very simple evaluation criteria, which is yeah. So I've taken these 3 criteria to evaluate our model. I hope it is visible. The code is visible, right?
Yeah.
Okay. So these metrics, there are 3 metrics. One is called exact match, the other is called function name accuracy, and the third is called parameter F1. So the exact match actually just matches the dataset output to the output of the model and figures out whether they are matching or not. Function name accuracy is so our dataset, you have to call multiple functions in a sequence in order to perform the accomplished task. So accuracy determines how what percentage of times the right model was called. And parameter F1 is the F1 score. Are you guys familiar with what an F1 score is? Okay. So each function needs certain parameters, and this F1 score measures the recall and precision of calling the right parameters in the right spots. So this evaluation code I have written in this function called calculate objective metrics, and I don't think we need to go through the code, but it is pretty simple in what it calculates. We can have additional evaluations like LLM as judge, or uh, uh, basically what is popular these days is that people also create a lot of environments. There are startups working on creating environments in order to test agents. So if you are creating an agent for computer use, a computer would be a very good environment. So that could also serve as a very good evaluation criteria. So this is the evaluation script. I will show you how to use it. It does some other stuff as well, querying the model, loading the LoRa adapter, but we'll come to it when we are actually running it. Now let's come to the inference part. So yeah. So in TensorFuse, whenever you are trying to deploy something, you just need two things. One is the Docker file or the actual code that you want to deploy. And the second is the deployment configuration that you want to use. So for instance, here I am asking asking TensorFuse to run model on one GPU on an L40S type of GPU, and I want the minimum and maximum scale to be 1. And these are certain other configuration settings that we don't need to get into right now. But essentially, this deployment.yaml file deals with specifying everything from the kind of auto load balancing strategies you need, the kind of auto scaling that you want to do. Everything can be defined here. By default, TensorFuse selects the best ones for the use case that you are doing. So for instance, we are deploying vLLM right now. So it would pick that you need to use throughput and ITL metrics in order to scale. If you are deploying a voice server, TTS server, those metrics would automatically pop up. And then we have a very simple Docker file. So to enable HFZ, I have added certain environment variables, and I have simply run a Python command to start vLLM. Now, we would be running vLLM with LoRa enabled. So we are training a fine-tuned LoRa adapter. We need dynamic uploading of LoRa's when the model is running and the actual inference is happening. So for that, we have added two changes, which is one is an environment variable to run LoRa. And in vLLM, you need the enable LoRa command. And we have also added an API key called test, because in most production deployments, you would need your deployment behind an API key, behind an authorized deployment. So here we have just put it in test, but we can use any environment variable or a secret in order to run the deployment. So yeah, we are at 81%. This should. So is everyone able to follow till now? Any doubts, any questions? No. Okay, great. So now moving on to fine tuning. So this is slightly tricky. So I would follow it up line to understand. So to fine tune your models using axolotl, you require an axolotl base config. And that base config, each and every model provider actually releases an axolotl config if you want to fine tune them. So this is actually copied from the Qwen official fine tuning config that they have released. So I can quickly go over specific fields which ensure what we are trying to do. So the base model specifies the model that we are trying to train, which is Qwen 3B. Chat template. So every model has the way in which it ingests the messages that are coming to it. So Qwen 3 has its own chat template, so we are using the chat template. Here we have specified the data set that we want to use, the Hermes function calling v1 data set. And we have specified certain mappings in order to make it more palatable to the model. So for instance, we have mapped GPT and assistant both to a role called assistant, human and user to user, and a system to system. So these are how you want to process the dataset in order to make it compatible with Qwen for fine tuning. Then there are obvious hyperparameters like the validation set size that you want to use, the sequence length that you expect in your models. LoRa target modules is the layers on which you want to train your LoRa adapters for. So for instance, there would be a lot of layers in your model, but you want to target specific layers in order to modify them. So you would name those layers. These layers are easily available in the architecture diagram of a model. So 90% of the use cases, you won't need to modify anything here because these are the typical layers. So Q stands for query key value. That is the attention layers that we have. And these are the last layer projections that you have uh, 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 after the attention block when you have a fast forward block. So these are the last three layers that you optimize them for. Then, yeah. So in order to provide good logging and fine tuning observability, TensorFuse directly integrates with weights and biases as well. So here I have added weights and biases API keys and projects for my. I will also show you how to add for your use case, but I'll quickly go through how you can monitor. So yeah, our cluster is here ready. Everything is ready. So we can continue, but I'll quickly show you weights and biases as well in order to understand how we can monitor our runs. So weights and biases essentially provides these graphs where you can see how your training runs went, how your particular loss function behaved, how the learning rate varied, how the grad norm was. So everything is essentially tracked there. So we would be using this as well in order to run the fine tuning. So yeah, now that our cluster is complete, we need to set up. So is everyone able to follow till now? I hope everyone's cluster is set up. So once the cluster is set up, we need to follow these steps in order to sync the configurations and access rules to our laptop in order to deploy stuff. So let me start doing that. So yeah, first of all, let me.
You can ask if anybody is using Windows laptop or so this is supported on Linux and Mac. If you're using Windows or any other system, then probably either you can SSH into a Linux server or you can use WSL.
Yeah, WSL would work fine. A Windows subsystem for Linux. Let me just quickly. So I would recommend setting up a virtual environment with Python 3.11 or lower. If it is not available on your system, I have a guide to download Python as well. Is it? Yeah. You can download it from directly from here and add it to your path. But yeah, let me get started with these steps. So you can find the steps directly in your Tensorfuse account after your cluster gets completed. So let me just first create a virtual environment. And activate it. And let me install. So in the requirements text.txt, I have all the requirements. So these are very simple ones. OpenAI to query datasets requests and the TensorCube package. So I'll just quickly install them. So usually you would deploy via CI/CD GitOps based approach. So you would be setting credentials directly on your GitHub repo. But for the sake of this demo, we are going to do things locally. And that's why we need to configure credentials and configure SSO on our system and then run the commands. Otherwise, the typical production flow is to connect your repository to Tensorfuse, set up the AWS credentials there, and automatically it sets up the GitHub action. I have a guide. We have a guide for that as well on our docs. So if anybody is doing production deployment, you can just quickly set up these GitHub actions so that everything can happen from there. But for now, let's do it locally. Yeah. So yeah, all my requirements are installed. I'll just quickly check if TensorCube installed. Make sure you are on the latest version. 0.0.98 is the latest. So make sure that you are on that, and then you can start running these commands. So all the prerequisites that are needed to run TensorCube can be run using this install prerequisites command. This would install commands to locally run your system. Ignore the istio error if you are receiving it. That's because you are not connected to the cluster yet. That's why you are receiving istio error. But it would install EKSCTL, kubectl, everything you need to monitor it if you want to do locally. And then we'll set up an AWS profile in order to access our cluster. So the step to do that is to run AWS configure SSO, and we'll create a profile name called Tensorfuse. Let me just quickly create that. So now a lot of you might not be having identity center users. If that is the case, I have also added instructions. If you are not using identity center, you can start follow these instructions. But I am using identity center instructions, which is the recommended way to access anybody's AWS account. If you are stuck somewhere, please feel free to stop me or call Agam, any of you. So yeah, so when you run AWS configure SSO, it will ask for SSO start URL command. So the place to access that would be in your identity center. Let me just show you where to access these. So if you go to the identity center, you will see the AWS access portal URL. That's what it means when it says the SSO start URL. So I'll just add it there. I would add the region. The region can also be found here. So mine is US East 1. So I'll copy and run it. I can keep this at default, and then it would ask to authorize my AWS account. And once the flow completes, I will have to choose my AWS account. So whatever account you are running this tutorial with, just choose that and choose the right role that you want to use. And finally, I would recommend the region to be the one where you set your cluster. So US East 1 is the region where we recommended first. Most likely you would be running on US East 1, so you can directly set that up. Once we are set up with the AWS configuration, we can just we'll have to log into AWS, which will again run the authorization flow. And once you do that, we are all set. We are now ready to deploy. We just have to sync the permissions to our local environment. So let me just log in to TensorCube. Yes, and then run TensorCube sync. So all these steps would be not necessary if you are running a production cluster, because GitHub flow would take care of that, but we are doing it locally, so we are running it right now. So once you perform all these steps present on this screen, we are ready to deploy. I'll wait here 5 minutes. If you are facing any difficulties or want any clarification. So what this TensorCube thing does is gives your terminal permissions to actually give commands to your cluster and deploy things there. So I'm assuming everyone is at the same page and I'm going forward with it. So now comes the important bit. So yeah, so let's actually start deploying and fine tuning the models. Yeah, so let me open up a terminal here. Activate my virtual environment and move to Inference. A quick sanity check if your setup is ready is to run TensorCube version. So it will tell you which CLI version you are on right now and what is the cluster version that you are running. So for me, both are at 0.0.98. If you have configured it today, you would be at 0.0.98. So this is a good enough sanity check. And I would do it again here to see if I am able to access TensorCube here. Yeah, I am able to. So now let's run let's deploy the one. So as I said earlier, we have two files, Docker file and deployment.yaml. And in order to do this with TensorCube, you just need one command. You can do TensorCube deploy -- config file deployment.yaml. I'm taking commands from here. So let me just copy paste, okay, so that it doesn't seem out of the place. Oh yeah, sorry for that. Yeah. So any production level deployment, the key part of it is how do you manage your secrets and how do you transfer it to the pods or your deployments. So right now, we would be downloading models from Hugging Face and we would be uploading our LoRA adapters to Hugging Face. So we would have to create a Hugging Face credential as well. So in your Hugging Face account, I want you to go to settings, access tokens, and create a new write token. So just create a token here and just copy the token for later use and paste it somewhere. We will use this token to access the Qwen 3 model and download it. So once you create the token, you can copy this command to store it in Tensorfuse. So Tensorfuse supports storing secrets by environment. So secrets, whenever you want to pass credentials to your deployments, you would use something called secrets. And whenever you want to isolate your deployments, you would use by creating different environments. I'll come to the use of environments, but right now let's create the Hugging Face secret for our models to work. I'll just copy this command. Make sure you replace your Hugging Face secret here. So let me just do that. So I have just taken this command and I have replaced my Hugging Face token and put it in here. So once I do that, it would create a Hugging Face secret for me. And then to do a sanity check, I can also list all the secret currently present in my environments. So I can see that my Hugging Face token is available as a secret. Now you won't be able to retrieve this secret because secrets are supposed to be opaque. So once you create the secret, you won't be able to see it or verify it. You would be able to change it, but you will have to do a force update because that secret is connected to your deployment. So I'm not covering that flow here, but yeah, your secret is created. Now you just have to do is run the TensorCube deploy command, and your deployment would become ready. It would run some pre-flight checks to see whether your cluster is ready for deployment or not, and that's it. So you need a deployment.yaml Docker file, and then you run TensorCube deploy. It would create a deployment for you. Now, behind the scenes, Tensorfuse is doing a lot of heavy lifting for you. I will just quickly cover what happens when you run a build. So typically, I have here shown client to be CLI or GitHub action. 90% of the cases, it would be GitHub actions on production deployment. So once you run TensorCube deploy, what TensorFuse does is it submits a build job, which creates an optimized version of a container image. So earlier I told you that we created a different kind of snapshotter in order to solve for cold starts. So that snapshotter actually requires a different OCI spec than the normal container file is built on. So this will submit a job to build your Docker file for that optimized config, scale up instance in order to run the build job, and then create an ECR repo. ECR is Elastic Container Registry, which is like Docker Hub within your AWS. So it would create the optimized version and upload on ECR for further use for versioning and everything. So this is what happens when you submit a build job. Once this build is complete, an entire inference stack would be served, which would look like this. So there would be a load balancer. So a load balancer, as I said, which would take into account the KV cache utilization and the queue length of your vLLM server in order to direct requests to different servers, different pods. It would set up auto scaling spec on Carpenter. So Carpenter is one of the very popular open source auto scalers. So it would configure Carpenter to look at your TTFT and throughput metrics in order to start more instances. And it would pull the image from ECR and put it behind a Knative serving endpoint, which would give you an endpoint at the end. So all this process would happen just by running that command. Okay, something went wrong. Let me just see. Oh, I have to log in on this with AWS SSO. Okay. My login token expired. Let me quickly log in. So all these SSO credentials are very short-lived credentials, which is good, so that they get destroyed as soon as your use case gets over, and in case they get leaked, so nobody can use them. That's why it is always good practice to use identity users instead of SSM users. So yeah, let me just run again.
Version we are going to try.
Is the cluster created or? Oh, okay. So you use kubectl.
I think so. I seem to have had.
So that's the reason it was.
Yes.
Okay, the cluster.
Yeah. So we are just working on. Okay, where is?
Yeah, we're at this step. We will do this and basically do another.
Yeah, so can you go there? It will automatically handle it. Go back to the app.
The app, the Tensorfuse.
Yeah. And continue. And just can you?
Meanwhile, this is running. We can
This is
also
where we are.
start setting up the
Because I
Finetuning,
took it CTL
pipeline. So this would actually complete the build step, push to ECR, and give a deployment.
we did, but even
Okay,
then
so it has
is
started. So what happens is first your code is uploaded to an S3 bucket, and then the build process would happen. And once the build is complete, it would start serving from your ECR repository. While this is getting deployed, so the build takes quite some time, around 5-6 minutes, because a GPU image has to be built. This building, let's also set up our fine-tuning pipeline so that we can run and experiment fine-tuning servers.
Yeah.
So let me quickly open up a new terminal. Activate my virtual environment.
Okay, we'll figure out how to uninstall it. We'll probably need help with the steps after that.
Yep. So I'm already logged in. Good. So now, let me go to the fine-tuning folder. So for fine-tuning, we have an axolotl base config, train.py file. So what the train.py file does, all the basic settings of our fine-tuning are already present on this axolotl config.yaml. So we have set up what LoRA rank to use, what LoRA alpha to use. Then we have number of epochs also set, micro batch size set, gradient accumulation step sets. We can also modify the optimizer that we want to use. So we are using the best settings right now, but all of these are configurable, and I'll show you how to configure them as well. Right now, we are using a learning rate scheduler, cosine learning rate scheduler, which basically increases and decreases your learning rate in a cosine fashion. And we have some values for learning rate as well, and some warm-up settings. So these are all the hyperparameters that you can modify if you're not satisfied with your fine-tuning runs and you want to test other things. There is this axolotl train.py file, which basically starts the fine-tuning in your environment. And before doing that, it basically overrides any hyperparameter that you want it to override. So I'll show you how it does that. But this recursive update function actually does that. It takes your base configuration, gets in the parameters that you want to update, merges them, and starts the fine-tuning them. And the Docker file for this is very simple. You just install Tensorfuse and PyYAML on axolotl and copy the train.py files and config files and run the configuration. So what we are trying to achieve from this fine-tuning pipeline is to have a base the base fine-tuning job ready, which can train Qwen 3 on any dataset and any configuration. Once this job is deployed, we would be sending in hyperparameters or the dataset names or any of the keys that were present in the configuration file in order to update them, so that we can, with the same infrastructure, we can run multiple types of training on multiple different datasets. So that's the goal that we are doing. So let me quickly. So before jumping, I will quickly show you how this looks on the EC2 console. So if you go to the EC2 console in your service, you would see instances. So these two are the base instances on which Tensorfuse's runtime runs. This is the build process that is running on an R5 instance. And once your deployment is ready, once your fine-tuning run starts, you will start seeing different instances here. So this shows you that it can support multiple heterogeneous types of compute and how the auto-scaling works. So yeah, let's return to our guide and set things up. So again, now comes the isolation from environments. So you never want to set up your fine-tuning and inference in the same environment. That's because if people start submitting multiple inference requests, your fine-tuning might get overshadowed. Or if your fine-tuning runs are not that important, they might throttle your inference capacity. So it is required to isolate them. By default, we always isolate your fine-tuning runs in a separate environment called Keda. It is called Kubernetes Event-Driven Autoscaling. So that's the name of the environment because that's the process that autoscales it. So we will need to copy the same Hugging Face token that we created and replicate it here so that there is isolation of secrets within environments as well. Let me quickly create the Keda environment, the secret in the Keda environment. And then, as I showed you that we can also integrate with weights and biases for easy monitoring. So let me quickly show you how to grab your API key. So in weights and biases, you can go here, you can visit your API key. Let me just sign in. Yeah, so this is your API key, you can copy it and use in the place of the WAN-DB API. So this would integrate your fine-tuning runs with weights and biases directly. Let me quickly do that. So I'm using my weights and biases API key and creating it in an environment data. And then, yeah. So once these are done, we are ready with uploading the models on Hugging Face because we have Hugging Face light token ready. And then observability for weights and biases. So fine-tuning involves two steps. As I said, there's a base job, which deploys the base configuration. And then job queues in which we can keep on submitting different hyperparameters, different data sets so that we can keep on running. So let's deploy using this command. So to deploy a job, you can run TensorFuse job deploy command. And I'll explain what I'm doing here. So I've given it a name by the -- name parameter. It's called Qwen fine tuning. I am giving it a configuration to use one GPU and the GPU type is L40S. Now L40S comes with 48 gigs of GPU RAM and it is optimal for training 8 billion parameter models up till 27 billion parameter models you can train on one GPU. If you were to train 70 billion parameter models, we would have changed the / GPU slack to 2 or 3 or 4, whatever we wanted. And Tensorfuse will take care of setting up the communication between the GPUs and communicating gradients and activations and stuff. And then we have added our two secrets, Hugging Face secret to upload the train LoRa adapter to Hugging Face and the weights and biases secret in order to monitor the training run. So let me just do this. Meanwhile, our build is complete with the deployment that we have. It is right now exporting the optimized image to ECR so that you can use it in multiple places and do versioning as well. So whenever you run an execute command, it has to do a lot of security checks before it actually runs the command, so that it knows whether you are the right principal who has access to change the deployment or resources. That's what's happening right now. We'll return to this. So I'll quickly show you what exactly happened when you deploy a job. So first, when you deploy a job, the build process is very similar. You build an optimized version of the image, submit it to ECR so that your base job is ready. And once that is done, we have an SQS first in first out queue that automatically gets configured along with a DynamoDB dataset in order to manage your job statuses and priorities. Jobs can have multiple priorities. There usually are video and image customers. Usually run free tier and like paid tiers for their subscriptions, and all the paid tier jobs are priority jobs. so that whenever a paid tier job comes up, all the free tier jobs are actually eliminated from the queue and the paid tier jobs get submitted. So this is the entire infrastructure on which it works. So a simple FIFO queue, which basically stores the parameters and messages, and a DynamoDB, which captures the status of the job, how long it ran, what is the priority of the job, and Keda listens to the FIFO first in SKS queue in order to make scaling decisions on the basis of what kind of GPU the job requires and how many GPUs it needs. So all this happens behind the scene when you deploy a job. So yeah, our job deployment also has started. It would build the image and deploy it. So you see our build process is uploaded the optimized image to an ECR repo. I'll quickly go ahead and show you where that is. So if you go to ECR, yeah. So the name of our job was Inference, right? So Tensorfuse Inference is the image that is deployed. So technically we manage versions till 4 or 5 revisions, but you can configure it to handle a lot more history. Just to save money on the storage, we do this. And it's if you see, it's a 10 GB image, which is quite huge, but because of the snapshotter, it will get downloaded.
I can't because I don't have the. Yeah.
Okay.
Serving in.
So I'll also again go back to.
And I just want users to have access to an endpoint that enables them, and when they call this endpoint,
auto scale.
It serves this model to them.
So yeah,
I'd love to.
Since our build process completed and we use an L40S GPU, you would see a G6C.xlarge machine starting to come up. That's where the inference job would run.
And my name is Mohammed.
So yeah, it has started. And if you can see the image pull time, let me just comment. So you see successfully pulled.
Monday might be bad unless it's. Tuesday is also kind of bad. Would it be? Well, yeah. Tuesday I think is better. Yeah, let's do Tuesday.
If you see this log, you will see that the image got pulled in 1.02 seconds, and the image size, as I showed you, was around 10 gigs. So if you wouldn't have used this snapshotter, you would have waited like 15 minutes in order to download the image and start it up. So now the model download process.
Can I add one of my other emails? I also add my colleagues.
Which is again vLLM's responsibility, while the image build process would happen on the fine-tuning pipeline. While this is happening, I will quickly show you what all things can be done with Axolotl. Yeah. So now that the entire thing, fine-tuning and inference is made, I just want you to know how we can modify the base config in order to run things that we want. So Axolotl supports a lot of different fine-tuning workflows. So supervised fine-tuning is something that we are running right now, but it also supports reinforcement learning and GRPO pipelines by this TRL config. So this is the entire configuration file that you can modify in order to run Axolotl, but I'll focus on the most important bits. So for running multi-GPU training, the most important part is FSDP, which is called fully sharded data parallel. Yeah. So you can have an FSDP config which can run this training workflow on up to 8 GPUs. If you want to go beyond 8 GPUs, you would need a multi-node training setup, which would require again certain extra additional setups to do with Tensorfuse. You can also
in order to
modify the vocabulary of a
properties
model.
that are more.
So in order to modify the vocabulary of a model, you would need to add special tokens. So end of sentence, adding
people would have control.
unknown token.
They would be able to debug it.
Sometimes
and they'd also be able to intervene.
word in a foreign language cannot be translated to a known vocabulary element. So that's what unknown token is for. And you can use additional special tokens in order to list everything. Then there are steps to modify. So number of epochs and maximum steps is the most common setting, where how many epochs you want your fine-tuning run to run through the data set. Warm-up steps means, so in fine-tuning, you don't want to start with the exact learning rate. You need to slowly warm up your gradients till the learning rate reaches its maxima. So that's what warm-up ratio and warm-up steps refer to. And then you have
we're just looking for a serving infrastructure when we release the
LoRa settings. So yeah. So LoRa, these LoRa settings control how
I want to say it's
many
either
parameters that you want to
I don't remember exactly.
So think of LoRa rank and LoRa alpha as the two most important hyperparameters that you would vary when you want to modify your fine-tuning runs if you are receiving a very low accuracy or very poor loss. The larger LoRa R means you are training bigger matrices, and
we like using H100.
And the larger alpha means their dot products will have additional dimensions, which would be trained. And there would be essentially two matrices, A and B, which get combined. So LoRa R and LoRa alpha control the dimensions of those two matrices. And the final bit is QLoRa. So QLoRa stands for quantized LoRa. So what we are running today is a quantized version of LoRa, where all the LoRa parameters are not 32-bit, but they are quantized to 16-bit or 8-bit or 4-bit. So right now, if you want to run LoRa fine-tuning on very large models like Llama Scout, which is 109 billion parameters, it is recommended to use quantized LoRa instead of normal LoRa. So these are the LoRa functions. Now LoRa dropout and LoRa target linear. These are very advanced versions of using LoRa. You would never need them, but they control. So there is this thing called regularization in machine learning. So regularization means that you are constraining the number of dimensions or number. You're constraining how much the weights can be trained, so that you don't break the training or you don't go outside the. Your losses suddenly don't become high and you don't cross the local minimum. That's called regularization, and LoRa dropout is a way to control that. It essentially drops out certain parameters from your matrix in order to provide regularization. So yeah, these are the main configuration options that I wanted to cover, but there are hundreds of configuration options that you can verify and use. But most foundation model releases already come with a LoRa configuration. So I'll show you quickly. Yep. So if you go to Qwen will always give you a LoRa config. Give me just one second. Okay, so if you go to Qwen's official doc, there is always a QLoRa config that they release with their standard version. Same goes for Llama, same goes for Llama, any frontier model Mistra. So they would always release an axolotl config, and what you can do is blindly copy this, change the data set, change the number of epochs and number of steps, and you are good to go. So that's what we are doing right today. So the configuration that you see here is actually this configuration modified for the 8 billion parameter. That's it. So if you will see, our inference server is ready now and it can start serving requests. So let me quickly show you how it looks on the deployments page. So this is our deployment, which comes with an endpoint. Now this endpoint is AWS load balancer endpoint, so I wouldn't recommend to use this directly in production. There is a guide to configure custom domains with TLS, which you can follow later. But for the sake of this demo, I'll use this in order to do the run the demo. Now, so this API endpoint is OpenAI compatible. So you can call the V1 completions endpoint on this in order to run inference. So let me see if I have, okay, so B1 dash models. This is an example curl request, which you can see for sanity check whether your models are working or not. So since we used the test as an API, I have to put test in the authorization header. If we do, yeah, our deployment is working, and currently we just have 23 8 billion parameter deployed. Once we load our LoRA adapter,
that kubectl issue.
Yes.
once we load our LoRa adapter, we would be able to see the LoRa adapter being listed in the list of models as well. So now what I want you guys to do is to copy this API endpoint, and in the evaluation script, you can just substitute your app URL with this endpoint.
Yeah, just curious, how many of you are waiting on limits? CPU, vCPU limits? The person who's approving them is just nowhere to be seen, so they're just being stacked up. So I apologize.
Most of them are waiting for the GPU one.
Yeah, I mean, any limits. GPU, vCPUs for.
I think a lot of them have already created the cluster. I could see like 4 or 5 people have already clustered.
Okay.
So once you replace it on the evaluation script, you can run it on the data set as well. So what I'll do is I'll quickly run it on like 50 samples and see how well it performs. I'll also ask Perplexity to actually create an inference URL. Let's do that. Let's first check if it is inference. I'm very bad at creating curl requests. I'll just ask Perplexity. Let's try this. Try with stream true first, so that you can see if streaming is activated by default or not. Streaming is active. If you'll see in stream, what it does is it basically streams a single token. This is just this is who these tokens. The streaming is very important in voice use cases because you transcribe as and when tokens come in. Now let's try with an stream false and see. So stream false will take some time because it generates all the tokens simultaneously and then returns a response. So yeah, once upon a time, two brothers, Jack and Mike, blah blah blah. So this our inference endpoint is ready. Now let's put it and run it on 50 examples on our data set. So here I have some settings which you can play with later on. Change the number of concurrency, base URL, and other things which you can do. Right now, in order to run this, you just and then let me run the evaluation script. So evaluation script does two things. First, it asks you whether you want to load a LoRa adapter or not. And okay. It asks you whether you want to load a LoRa adapter or run evaluations on them or not. You would load a LoRa adapter once I've. Okay, so now let's pause and just submit a fine tuning run so that we are ready by the time I do the experiment. So, as I said, we are deploying a base job, and then we can modify that with other configurations in order to run the fine tuning. So what I'll do is I'll go ahead and copy this command to submit your job. Let me just first paste it here and modify things which we can. So this command basically has three things. The job that you want to run, if you remember, you have the job ID that you want to give it, so that you can identify different runs, and all the payload, all the things that you want to modify in the original configuration, you just give it as a Python bit or a JSON file. Yeah. So for instance, let me just, okay, so this is the JSON string, which will go ahead. So if you see our configuration, there is this base model, hub model ID, all these keys. So what I am doing right now is modifying the hub model ID. Set my account. What I can do is I can set my base account. So this is my and here is where the upload will take place. This repository is where the uploaded to. I can modify the number of epochs to run multiple times. Let's run it for now because otherwise the training run will get longer. I can modify the learning rate and any number of things that you want to modify. Okay, inside the JSON string and pass it to the payload. Let me also modify the OnDB entity. So weights and bias entity is the name of the account that you are using to run the weights and biases. Let me quickly copy my entity. It would mostly be your username and or your team name if you're using a team account. So let's do that. So we are ready. So I have modified the hub model ID to upload it. And the one just copy it. So meanwhile, you can also view these on the dashboard. Right now, we have just one job, which is queued. The run one job that we submitted, it got queued. We can also check it using CLI as well, what jobs that we have submitted and whether they are in running state or queued state or processing state. In some time, it will get queued. It will start running the fine-tuning process. Everything is configurable, how many jobs to run parallelly, how much time to take between jobs, how long should a job run before it should be shut down. All these settings are pretty easily configured. So now we have, so this is how we submit a fine-tuning run. Whenever you want to modify or run on a different data set, what you will do is you will just copy the data set's path key and change the function calling here, paste it here, and submit it. This is not the ideal interface.
Again, CLI is not how you submit jobs. Most people, what they do is programmatically submit jobs. So there's an API which is calling the job to submit the job. I'll show you how that works. We have docs around that as well. So, uh, so typically what you would do is, so let's say you are running a video generation company. So customers will come to you and will submit a request to create a new video. What you will do is you will just call this Q new job pipeline with this payload. Job payload is just a Python string there. This is looking tedious because we are using an interface which is not fine-tuned for that. We are using a CLI interface, but that is not how you do things in production. Okay. And I've shown you examples of fine-tuning for job queues, but job queues are used by our customers for almost every batch functionality possible. So we have one customer which processes lots and lots of clinical trial data, and their usually model runs on weekends. So Friday at the end of the day, patient records are submitted for clinical trials. They run a batch job which runs for 6-7 hours and goes down. So that also happens via job queues. This is an example of how just a fine-tuning run happens via job queues. And yeah, so let's quickly check the status if it has started processing. Our job is in processing state, and within 2-3 minutes, it will also start reflecting here. Right now, Gemma run is there, but within a few seconds, as soon as it starts generating logs and graphs, it would start showing up here. I'll bring it to you. So yeah, meanwhile, this is running. Let's go back to evaluations. Now, yeah, as I was saying, there are two things that can be done: loading a LoRa adapter and running evaluations. We'll load a LoRa adapter once the adapter is ready, but right now let's run evaluations. It would go through the inference server and figure out what all models were there. Right now, we just deployed the base model, but as and when we'll dynamically add LoRa, all the LoRa list would start coming up. So we can do this. Let's run on all models for now. And it would start running on the Qwen 3 dataset. Now, what we can do is we can also see logs of the services that are being deployed in order to see how fast vLLM is actually processing our requests. So what I would do is I would just run Tensorfuse deployment logs. Service here. It would start streaming jobs. So right now I'm running at maximum verbosity. So you would see what vLLM does to the request. So this is the entire request is being logged, and vLLM has several processes where it adds request to queue, processes it, again does in-flight batching. So all these logs you can see here. Which email ID? And these are all the requests being completed. So these logs are visible. Same for jobs as well. You can view logs for jobs, and you can view logs here as well. So if you go to now we need to run requirements. So now there's a logs tab as well, which you can use to view logs. But the first time you run logs, it's a little slow because it has to fetch logs from AWS. I'll show you this once the logs are ready. So right, whatever command we will be running CLI. So ideally, let's see if our GitHub Actiontuning project starts. We just run GitHub runner and you just give the demo. What we're doing is create it. You just you need to run properly for CLI. So it connects. So it knows. I'll also show you an example of seeing the logs in the jobs.
The concern one thing is
as well. So Qwen to fine-tuning is a job. No, this has nothing to do with that. See the logs for the job as well, so we know how it is running. Your personal account, right?
Yeah.
Yeah. So,
okay, just that. But will be synced.
Exactly. This is how fine tuning happens in accelerators. It basically loads and logs all the parameters that are happening. So if you can see the epoch number, the eval loss, how much time it took to do evaluations, everything is being logged. And once it starts reflecting on
This is where all your deployment come now.
Yeah. So you see it has started reflecting here. And you can observe almost everything here on weights and biases. So if you want to see eval loss, training loss, since it has started, it will take some time to reflect, but yeah, everything is available here. How much GPU memory is being used, GPU compute being used, and at the same time, what the logs will also be printed here. So everything that is happening, you can monitor here and understand what is going on. All the artifacts will also be here, and these will also be uploaded to Hugging. So it's a very good information if you use all these things simultaneously. So you can see it is working with the the configuration values that we gave.
These are the files
for warm-up ratio and the learning rate that we mentioned rather than the one that was present in the.
This is our inference direct.
So
this is a vLLM based image that we are using. And you will need an Hugging Face token for this.
The eval script, if you see the base model, even though it is Qwen 3 latest, it performs very poorly on function calling benchmarks. There are a couple of reasons for that. One is because it is using a lot of thing tokens, so it cannot take in as much context. And if you see the func name accuracy and param-F1 accuracy, that is very low. Even if you go to larger models, 27 billion,
push it to your AWS account, the one that we have.
Function calling is very bad.
And view all your deployments.
That's why people either prefer using low code.
So it's basically a mix. So we want to see it mean not all your deployments will be.
Our customers use
working on the
fine tuning for function calling in scenarios where
authenticate your CLI with your AWS.
ChatGPT might not have seen their data. For example, one of our customers has served restaurants as voice agents. So they have a lot of restaurant menus which are very big. Sometimes they are very big. And they tried with GPT-4o, OT as well, but they were unable to make it function calling work. Now they are running function calling with a 3 billion parameter model. So if you see a 3 billion parameter model, it is actually able to match or defeat 4o.
I just wanted to make sure we didn't get access to something.
You are doing proper.
Even AWS SDK to do things.
Okay.
Tuning or proper training. Let me check. So we have started seeing the training loss go down and the learning rate. So we set up some warm-up steps. So that's why our learning rate first warms up and then gradually does a cosine. You can measure everything here and do the logs. I think logs will also get reflected somewhat later, but you can see the logs here. So while this is so this is how you can see the logs here as well. I know the readability is a mess slightly. We are working on improving it. See them here. Apart from that, anything. When it is training, I would like to take questions if you have any specific questions around the process, around when to use, what to use. Or was that just a lot of technical talk so you all are bored now? Okay.
Yeah. Installation.
Is your AWS CLI being used somewhere? Is it okay if I upgrade it? Do you remember how did you install this?
Any other version on Windows side, but globally,
You have to pay.
we use WS. For example, right now,
Okay.
why I wasn't sure.
That should be
I'm working on it right now.
Yeah, we can. Actually, I'm just looking a way for it to uninstall so that this can install. AWS CLI.
Oh, sure. I have a guide.
I'm not sure.
You guys reinstall it.
No, don't install it. Just uninstall it and run Tensorfuse install prerequisite. I think that would work. Let me just try removing the background.
So it's on a day-to-day basis.
Does it not need?
Not even
No, it needs AWS CLI, but you don't install the correct version.
any way for us
Doesn't
to
need to be.
configure the runtime there to depending on. Oh, that depends on what's there. Just straight to AWS.
We did it.
Try this again. This goes for a while, right? You should have a verbose option. You should have a verbose option.
Okay.
There's a lot.
Actually, yeah. Are you sure you want to finish the?
It said something about the meeting the AWS.
I've been
It
like
may
working
be-
all day, so my blood sugar just got up.
Recommended that it's installed.
So I was like,
Okay.
half
That's why
asleep.
it's all again,
Just
that's
try
for
my
spam.
I haven't had any food all day, so I get. But yeah, I'm sorry. You asked
Yes,
about
working.
my like how I work. Yeah, Windows. Basically,
It's messy for.
Are you a gamer?
do some
Yeah, I do some gaming.
That's why you are.
No, I have it because I do video.
Oh,
VJ.
video.
Okay, I do a lot of visualization. I have to do stuff dependencies are not.
Okay.
Change it.
Much stronger.
Type also.
I mean, yeah, it's just 26 years old.
You tried running models on this?
Not on the machine. No, I have a workstation.
Oh, okay. And we also launched that digits.
I don't know what to tell you. Like, that's
Yeah.
company wide. We use, yeah. We don't even have API access for that. Yeah, 100%. It's very small. I don't know how, but for some reason, there's a access.
Good presentation on
I'm gonna do that, but also I
Apologies for this.
I also
It's all right. It's my fault.
actually have a project. Yeah. So a lot of my clients are yourself. This is why it's like, oh, you see that. Yeah, so I have like products in India and we're actually building out a product.
It takes a while.
Then tracking.
And in the end, it's
It had a like a warning for something and then an error saying it couldn't.
So like trying to give it to the optimized.
It's doing this.
Instead of SSL to manual.
Gives you hope.
Yeah.
I'll come back.
Yeah, definitely.
I do like some of the work, but a lot of it is also. I think we do have and we do have accounts in how we're running our so once the pilot is running for like a couple of months. Right now for like phase either phase not and they're trying to see if this happens.
I'm still going. No, I'll let you know.
Sorry, I think what they're trying to do is what is the cost? Yeah, they're just trying to see if this is feasible. Of some other basics.
Oh, this is which Python?
I'm using 3.8
for AI. And then they were like, oh, why are you paying this for that? Why are we building the pilot up? And for us to maybe use. We have the action cost on my health and family as well.
No,
Doing that, and like really worked out. It was like, hey, you're gonna pay us to build this platform. This is like 2 words, 1 stone. We're getting paid for all the stuff. It's really good for us. That's what we're doing right now. I mean, all after we can get the stuff is already built. But then I don't tell you off the top of my head because I only work for.
it got installed or what?
Yeah, so I follow the steps, but then I start 7 a.m. today. Go through the install, all these things. Moving on meeting. And after that, I wanted to play. A lot of it with the client that we have as well. Switches. I think the rest of the world like split up. That's pretty good. So moving data from you know the international without I want to be like all the other because right there. But it's like the stuff that I work on. Also, I work on a lot of the AI like projects because partners at Times are entire platforms, the AI platform. So he likes to have a lot of the projects, something like to be doing. We're trying to continue take with the work with AI. For us, I think that when you write a control is just a way of if you're the audit guys to look at this is possible. Problem, they could give it any problem. Making users, like for example, you have to tabulate that, you have to get that. We're supposed to be SEC